Well, howdy there, Internet people. It's Professor Leach again. Today, we're going to talk about some important triangles that we just need to remember. And we're going to start with the isosceles right triangle. Isosceles, when we're referring to triangles, isosceles means just that two sides are equal. So isosceles just means two of the sides are equal. This includes that two of the angles are equal. So let's draw a picture of a triangle that fits this description. So in an isosceles triangle, the hypotenuse can't be the same as one of the other two sides. One of the things that we should always keep in mind is that the hypotenuse in a right triangle, that's redundant, the hypotenuse has always got to be the biggest side. In a right triangle, the right angle is always biggest, and sides opposite bigger angles are going to be bigger. Since these two sides, the two legs of this right triangle are equal, the angles opposite those sides must also be equal. Since we've taken up 90 of our 180 degrees in the right angle, that means these two angles are both 45-degree angles. Angles opposite equal sides are equal. Angles opposite equal sides are equal. Angles opposite equal sides are equal. Geometry facts. Also, if we increase this angle, the side opposite the bigger angle has got to be the bigger side. Bigger side, bigger angle opposite. So if I increase this 45-degree angle, that's going to stretch the side opposite that angle. So makes sense. But we need to state the things that, even if they might seem obvious, we need to state when that they are true. So the advantage that we have here is that if these two sides are the same, instead of saying A and B and C, I can give them the same name, A and A. And it's a right triangle, so I'll still use C for the hypotenuse. And then this will give us a relationship between the sides of a right triangle, of an isosceles right triangle. We can use the Pythagorean theorem, a squared plus a squared is equal to c squared. And this means that 2a squared is equal to c squared. And this means that a squared, or c squared, sorry, we take the square root all the way through. This tells us that c is equal to a times the square root of 2. So in an isosceles right triangle, we see that the hypotenuse is the square root of 2 times the legs of the right triangle. We can turn this around and solve for the a and just divide by the square root of 2. A is c divided by the square root of 2. So if we have a length of a is 10, then c is just 10 times the square root of 2. So for example, if I draw an isosceles right triangle, and I say that side if this is 45, and this is 45. If we're given that this side here is equal to 10, then we don't have to do any additional calculation. We can say this is an isosceles right triangle, and the hypotenuse C is just 10 times the square root of 2. When we write it this way, with the square root symbol, we are writing the exact value of C. So we refer to this as the exact value. So if you're trying to solve a problem and the problem says state the exact value, that means you're going to leave your square roots in there. Your calculator is not going to help you. The calculator is like, oh, hey, you need an approximation of that. It's like, oh, no, we need the exact values. And the calculator is like, oh, that's not my area of expertise. I don't know if you have conversations with your calculator. I don't know if I should be having conversations with my calculator, but it's just the way it is. So this is what we have with the exact value. If we grab our calculator, we are now looking at an approximation. So if we use our calculator, and say, hey, calculator, what's 10 times the square root of 2? It'll give us a 14.142. That is an approximation. Once you grab your calculator, you're looking at an approximation, no matter how many digits you write, because the square root of 2 is never going to stop. The square root of 2 is irrational. So if you use a calculator, once you punch in the square root of 2 on your calculator, you're looking at an approximation, no matter how many digits you write. So it's important to recognize as soon as you put an irrational number into your calculator, you're looking at an approximation no matter how many digits you write. I could write 50 digits after the decimal point, still an approximation. It's going to be a very close approximation, but it's still approximation. It is not exact. I could write 100 billion digits after the decimal point, and it is an approximation. A ridiculously way too accurate approximation that doesn't actually have any meaning in any kind of context, but it is not exactly the same. Right. So if we're given, we can see that C is the side times the square root of 2. So if we're given the C, if we have another triangle, I'm going to write it the other way because I almost never draw them this way. This is why they get all curvy. If instead I told you that C was equal to 7, and I want to know what A is in this isosceles right triangle, then A is just the hypotenuse divided by the square root of 2. So we would say A is the hypotenuse divided by the square root of 2. Here's the exact value. Any questions? And once again, we can grab our calculator and get an approximation of this value by taking 7 and dividing it by the square root of 2. And we get 4.9 50 to the nearest thousandth if I'm going to be consistent with my previous approximation. Or I could use 5 significant figures, 9, 4, 9, 7. There's an approximation. Once again, no matter how many digits I write. For the purposes of quizzes that I am scoring, it's okay to have radicals in your denominators. So I am okay with you having radicals in your denominators. Some algebra traditions do not like this because they don't realize we all have calculators now. And so it's kind of okay to have 7 over the square root of 2. So let's make a note of that.
For example, in Wiley plus, would the answer like that be acceptable, or?
I am not sure. Oops, 130. I am not sure if Wiley plus accepts non-rationalized answers. But some algebra traditions require that you rationalize your denominator. So in some algebra traditions, it is considered not simplified if there's a radical in your denominator. So rationalize means do not write radicals in your denominator. There are reasons for this that used to make sense that don't really make much sense anymore. I know the pro-rationalization traditionalists will be like, oh, Leach, you have to make them rationalize things. And I'm like, oh, no. To rationalize the denominator means the radicals are not allowed in the denominator. So we would have to simplify something like 7 over the square root of 2. To rationalize the denominator, we do our favorite math trick. We just multiply by 1. So what we're going to do is multiply by the square root of 2 over the square root of 2. So our trick is to multiply by 1, just like getting a common denominator. But a form of 1 that will get us what we want. What happens down here is we get the square root of 2 times the square root of 2, which equals the square root of 4. And then the numerator stays the 7 times the square root of 2. Can't really do anything with that. But the square root of 4 does not have to have a radical in it. The square root of 4 is just 2. So I can write this as 7 square roots of 2 over 2. No more radical in the denominator. This has been rationalized. So 7 over the square root of 2 has been rationalized. I'm not sure why I don't like, well, I know logically why I don't care about radicals in the denominator. And I also have maybe some reasons why I don't like it when people are concerned that there are radicals in the denominator. I don't know, there's just maybe too much context because it's like, Can't have any radicals, especially radicals in denominators. Radical denominations, eh? Coming up with radical ideas. Underneath, undermining. Let's square everything. So we turn our radicals into squares. And it's like, oh, that's just like, welcome to America. So you might have to, if you get 7 over the square root of 2 and Wiley plus is like, oh, no. It's like, oh, okay, let me rationalize that. And it'd be 7 times the square root of 2 over 2. And then Wiley plus will be like, oh, nice. For me, though, you can just write 7 over the square root of 2. If you're typing this into a quiz and you don't want to go into the equation editor, I don't know why you wouldn't want to do that. It comes out so cool. But to type this in syntax, you could say 7 divided by, the abbreviation for square root is SQRT, square root, and then what you're taking the square root of in parentheses. So 7 over square root of 2. So this is how you could type that number. To type this number out, to type this number without symbols, you'd have to take 7 square root of 2, then close parentheses, divide by 2. So here's how you could type this number, the rationalized version. If you drop a multiplication in between the 7 and the square root, that's okay. If you need that to help you remember that we're multiplying those things and then dividing by the square root of 2, then that's all right. Notice you need the parentheses after the square roots. So here I have 7 divided by the square root of 2. To calculate this, I would take 7 times the square root of 2, close parentheses, divide by the 2 to get the same thing. If we don't close the parentheses on the square root, we'll take care of the division first on some calculators. In this case, the Texas Instruments calculator does not require that you type times in between the 7 and the square root. It understands that juxtaposition is multiplication. But if you forget your parentheses, because the calculator types parentheses for you, it's going to say, oh, there's parentheses, so I'm going to do the 2 divided by 2 first. Square root of 2 divided by 2 is the square root of 1. 7 times 1 is 7. So you need your parentheses when you're writing things or when you're typing them on your calculator. Any questions? In case you're wondering why that is, it's because exponents are, radicals are exponents, and parentheses will change up the order. Parentheses says, do your multiplication and division before your exponents. So here's, let's look at our isosceles right triangle again. This was referred to in the text as a 45, 45, 90 triangle. And if the side, if each of the legs, which are equal, is just given a value of 1, then the hypotenuse will have a length of square root of 2. And because of how similar triangles work, if I multiply these by 10, I multiply the hypotenuse by 10. If I multiply this one by 7 over the square root of 2, then I multiply each of these by 7 over the square root of 2. What this allows us to calculate is the sine of 45 degrees, the cosine of 45 degrees, and the tangent of 45 degrees. So Sine of 45 is opposite over hypotenuse. So we have the opposite 1 over the hypotenuse square root of 2. Cosine of 45 is adjacent over hypotenuse, and because the opposite and the adjacent are the same, sine and cosine of 45 are the same. That's an important thing to recognize. Sine of 45 and cosine of 45 are equal. 45 degrees is where sine and cosine agree. Tangent of 45 is opposite over adjacent, so that's just 1. It's more common to see the sine of 45 because my radicals in the denominator are okay position has not been widely adopted. You might see the rationalized versions of sine and cosine of 45. So multiplying by root 2 over root 2, sine of 45 is root 2 over 2. Cosine of 45 is also root 2 over 2. So you should know those rationalized versions. Root 2 over 2. Any questions? These are 3 values that we should just remember. Sine of 45 is root 2 over 2. Cosine of 45 is root 2 over 2. Tangent of 45 is 1. As much as I favor putting radicals in the denominator and being okay with it, I was programmed when it was not okay. And so I remember sine of 45 as being root 2 over 2. It fits into a great pattern later, so we're going to keep the root 2 over 2. Any questions? Right. We should recognize the approximate values of root 2 over 2. So we should recognize the square root of 2. This is just 1.414213. We shouldn't know it that far, but 1.414, that we should recognize. And if we divide this by 2, we should recognize the decimal approximations. So root 2 over 2, this is the exact value. We should recognize this approximation of 0.7071 for both of them. In the same way that you want to recognize the decimal 0.5 as being 1/2, we're just expanding the number of decimals that you recognize. 1/2 is a 0.5, 1/4 is a 0.25, 1/3 is a 0.3 repeating. Square root of 2 over 2 is a 0.7071. It goes on forever, it never repeats or terminates. It's redundant. It never repeats, it never terminates. But we should recognize this as being square root of 2 over 2. This is our calculator trying to tell us root 2 over 2, which is also 1 over the square root of 2. Any questions? Let's move on to the other triangle that we have to recognize. And let's talk about the equilateral. Equilateral triangle. So equilateral means all 3 sides are the same. And what that means is that all angles are equal as well. And this should cause you some concern because you might be like, oh, dude, if all the sides are equal and all the angles are equal, that means all the angles are 60 degrees. Where's the right triangle on this? To which I respond, dude, don't call me dude. And second of all, it's fine if you want to call me dude. It's just weird. And second of all, I forgot what second of all was. So all the angles are equal as well. That means since there's 180 degrees in a triangle, all the angles are 60 degrees. And that's what we have in an equilateral triangle. Oops. So where's the right triangle? We have to cut it in half to get a right triangle. So we're going to cut it in half to get a 30-60-90 triangle, or a 30-60 right triangle. I think this book calls it a 30-60-90 triangle. So what we do is we just drop a vertical down from this one on the top or the one on the side. And that's where we get our right triangle. So our angle here is going to be 60 degrees. And I've cut this top one in half, so that's going to be 30 degrees. Also, if there's a right angle and a 60-degree angle, then the last one has to be a 30-degree angle. Now, if we go back to our equilateral triangle, I'm going to make all the sides equal to 2 for reasons, mainly because I want to cut this bottom side in half. And so this piece down here, if I cut this angle up here in half, I'll cut the side opposite in half. So each of those sides is going to be a 1. So what I have is a hypotenuse of 2. A side opposite the 30-degree angle is a 1. And I can use the Pythagorean theorem to find the third side. So 1 squared plus b squared is equal to 2 squared. So b squared is equal to 2 squared minus 1 squared. So b is equal to the square root of 3. Now I have the 3 sides of my 30-60-90 triangle. Right, so now we can use this to write down sine, cosine, and tangent of both 30 and 60. 2-for-1 deal. So now we can write down sine of 30 is, so 30 opposite is 1 and hypotenuse is 2. So sine of 30 is 1/2. A new thing that we have to remember forever. Cosine of 30, oops, forgot degrees. Cosine of 30 degrees is adjacent over hypotenuse, so that's going to be √3/2. And the tangent of 30 is opposite over adjacent, so 1 over the square root of 3. The rationalized form of 1 over the square root of 3 will be written as √3/3. Everything else seems rational enough. No other radicals in the denominator. So if I ask you for the tangent of 30 and it's a quiz, you can tell me 1 over the square root of 3. But if it's Wiley, I think you're going to have to use √3/3. So we should recognize all these approximations, although 1/2 is exactly equal to 0.5. So that's not an approximation. √3/2, that's going to be an approximation. So what's the square root of 3 divided by 2. So we should recognize the square root of 3 as 1.732, and the square root of 3 over 2 is 0.8660. So that's another fraction that we should recognize. And we should also recognize 1 over the square root of 3. Or you should remember it, you can remember it as root 3 close parentheses over 3. 0.5774, we'll call it. Once again, just more fractions that we want to recognize with their decimal forms. So we have sine 30, cosine 30, tangent to 30. There's also a 60-degree angle in here, so we have to write those down as well. The sine of 60 was 60. The root 3 is now opposite. Cosine of 60 is adjacent over our hypotenuse, so in this case, 1 over 2. And tangent of 60 is opposite over adjacent, so now that's opposite root 3 over adjacent 1. So it looks like when we went from 30 to 60, the sine and the cosine switched. That's an important thing to observe. The sine and cosine of complementary angles will always be equal because the opposite of one will be adjacent to the other. So sine and cosine of complementary angles sine and cosine of complementary angles are going to be equal because the opposite of one angle will be the adjacent to the other. We should recognize the square root of 3 as 1.732, we'll call it. Any questions? All right, so we've got to find a way to remember these values. One thing that's handy is that 30, we got to remember 30, 45, and 60. That we want to remember sine, cosine, and tangent of 30, 45, and 60. For sine and cosine, we want to notice how organized things are. There's a 1 over 2, a root 2 over 2, and a root 3 over 2. So the numbers that are running around for sine and cosine, root 1 over 2, root 2 over 2, and root 3 over 2. Tangent has 1 for 45, that's in the middle. The smaller one is 1 over root 3 at 30. Tangent of 60 on the other side is root 3. So tangents, we have reciprocals of complementary angles. Tangents of complementary angles will be reciprocals. Any questions? All right, so your job between now and next class is going to be finishing up chapter 1. And that includes remembering sine, cosine, and tangent of 30, 45, and 60. So 9 numbers that I want you to remember. And it has to be very fast recall. I don't want you to have to picture the triangle to come up with the values. I want to be able to say the cosine is 60 and you instantly respond 1/2. Just like if I ask you what 7 times 8 is, I don't want a big pause where you're like, oh, 56. I don't want a big pause where you're thinking about 7 rows of 8 objects and then counting all those things or grouping them into 5 10s and 6 1s left over. Any questions? Comments? All right, that's it for today. So anyway, it's just a thought. Y'all have a good day.